In this video, I'm going to give you a little bit more information about work, potential, and equilibrium, which I think is not really covered in the textbook very easily, and it gives you a good sense of how to connect the work and the potential energy along with forces and equilibrium. So the starting point is going to be equation 6.28, which gives the force in the x direction as the negative derivative of the potential with respect to x. So the first thing I want to do is just rearrange that, so I have du, and then I want to integrate that. And then we get something like this, which is just integrating from the initial potential to the final potential when it goes from x1 to x2. This thing, of course, if you did the fundamental theorem of calculus, this thing is just delta u. And we also want to compare this to work. So earlier in the chapter, we gave work as the following definition: the dot product of the integral of the force over the displacement. So in one dimension, of course, this is just fx times dx. And then just by comparing that guy to that guy, we can see that the work is the negative integral of the potential from the initial to the final, and this is actually negative change in potential. So this is expression 6.23 in the text, and actually the text points out that this is actually the internal work being done on the system. So to make sure that we actually understand this, let's do an example with the gravitational potential. So the gravitational potential, UG, at a certain location is mgh. So let's consider lifting an object in the gravitational potential field of the Earth. So the potential energy at one location is going to be mgh1, the second location is going to be mgh2, and I want h2 to be greater than h1 so that I'm lifting between the first position and the second position. Well, then the change in the potential energy is going to be mgh2 minus mgh1. Just writing like this, you can see that h2 is greater than h1, and so this thing is going to be greater than 0. And so the work, which is negative the change in u, that thing is going to be less than 0, which is what we expect because I'm lifting against gravity. The distance, the displacement of this object is in the positive y direction, say, but the gravity is pulling in the negative y direction, and so you get a negative number for the work, and that's what we expect. So this expression does exactly what we expect it to do in the gravitational field. So returning to our original equation, which is that the force is the negative derivative of the potential with respect to the position, this gives us a relationship between the force and potential which is similar to the relationship between position and velocity that we had in kinematics. Specifically, the slope of the potential is the force, or more technically, the negative slope. Because this is a negative sign, so if the slope is positive, then the force is actually negative. So just as a quick example, if this is our potential as a function of x, we can find the slope right here, and the negative of that slope is going to be our force. So in this case, force is going to be less than 0. And if we have a particle which is in here, it's going to experience a negative force, and therefore it's going to start moving back towards the origin in this case. Okay, well, what can we do with that? Well, we can actually learn something about equilibrium. So consider the following plot of potential versus position, and I want to know what's going on right at the bottom right there. So the slope right there is going to be 0 because it's flat, but of course that means since the slope of the potential is the force, this means that the force is going to be 0 there. And that means that that's an equilibrium position. Essentially, that means that since there's no force, there's no acceleration, this object will stay stationary as long as it's got no initial velocity. Further, we can think about what happens if the particle goes off of this point, further up the potential. So for instance, right up there, the slope is going to be positive. That means that the force is going to be negative, and the particle is going to want to move back to the center. Same deal over here. Slope negative, force positive. So right there we will have a force pushing the particle back to the original position. So no matter where the particle goes away from the equilibrium, it turns back and tries to stay right there. So this is called a stable equilibrium. We can check out what an unstable equilibrium is as well. So this is going to be an unstable equilibrium. How can we tell that? We can use the same arguments that we used for the stable case. First, the slope is 0, which means the force is 0, which means this is an equilibrium in the first place. Here we have a negative slope, so we have a positive force, and the particle wants to go there, away from the equilibrium position. On the other side, we have a positive slope, negative force, and the particle wants to also move away from the equilibrium position, so no matter what happens, the particle wants to go away from the equilibrium position, and this is called an unstable equilibrium. So notice that I'm still calling these equilibriums, because the particle will, if right here, have a force of 0, right here as well, a force of 0. So the particle, if sitting right there, will stay right there, no matter what. But in this case, if it's perturbed a little bit and goes up or down the potential, it will return back to the center. But here, if it's perturbed a little bit, it'll just go whoosh, start here and go whoosh. So of course, there's a place in between these two where the slope is 0 for more than just a point, but is 0 for a whole distance. That's something like that, like a flat top. The slope is 0, but it's 0 this entire way. So even if I go far away, I still feel no force, not until I get to the edge. So across this entire plateau, I feel no force. And this is called neutral equilibrium. So the particle, if it's moved a little bit, doesn't feel any desire to go back to the original position or any desire to go further away until it gets very far away, and then in this case it feels a desire to go away. But right here we have a neutral equilibrium. So if you remember anything from your calculus days, you will recall that what I'm talking about here is actually the second derivative of the potential, the first derivative being right here. But whether this thing is turned upwards, turned downwards, or flat depends actually on the second derivative. The second derivative being positive is the stable case. The second derivative being negative is the unstable case. And the second derivative being 0 is the neutral case. Okay, so the lesson to take away from this is that just by looking at the graph of the potential, you can figure out the stability of the force, where the force is 0, where the particle will feel no force, and whether that point is stable, whether if you push the particle, whether it will keep moving away from there or whether it will return. Of course, this isn't taking into account any velocity. This is just sort of figuring out the acceleration. So the particle could be moving in some way, some constant velocity, and not be affected by this at all. But this is the definition of equilibrium. It has to do with whether the particle is accelerating or not. And that makes sense. If a particle is moving at a constant velocity, it is natural to call that an equilibrium because the particle is not changing its motion in any way. It's moving at a constant velocity. Okay, thank you guys.